So good morning. My name is Christian Feld. I'm working at Jülich Supercomputing Center for several years now, and I'm developing the SCORP community measurement infrastructure. And today I'm talking about some introduction to parallel performance engineering to get the terminology right. So you might think that performance is a new problem, but that's not true. So some 200 years ago, Charles Babbage tried to build the first computer-like machine, the difference engine. He wanted to use this to approximate some functions with polynomials. And even at that time, he was very concerned about performance. So the most constant difficulty in contriving the engine has arisen from the desire to reduce the time in which the calculations were executed to the shortest which is possible. So here he has the metric time as his most important metric, and this also then drove his design to what in the end was the different engine. Unfortunately, building this engine, he didn't succeed, but it was built, I think, in the last century, there was a successful build of this machine. Okay, in the good old days before 2004, there was something that was called free lunch. So if you have an application and you want to improve the performance, you just have to wait until the next CPU came out, because at that time the number of transistors on the CPU doubled every 2 years, and also the clock frequency increased constantly, which you can see in the diagram. But from 2004 on, the hardware vendors realized that it's not possible to increase the clock rate any further because of the heat dissipations. You could not cool the systems, and also you could not provide all the energy needed for huge computer systems. So from that time on, still the number of transistors doubled every year, but now you have not only one processing unit, but several. So it started with dual-core CPUs, and so now with the Xeon Phi, for example, you have a processor which has more than 60 cores on it. So, and you have to program these cores, so you have to go parallel, and also the applications became more difficult, or what you want to get out of your simulation. So now you have multi-physics and multi-scale simulations. For example, you have coupled atmospheric models that are much more demanding to the software side and also to the hardware side, and you have to do this in parallel. And so basically this means that this free lunch that you can just wait for the next hardware, for the next new machine, is over, and you have to do much more on the software side. Okay, and what was also a new phenomenon is that if you increase the scale, so if you started with 512 processes, and now you want to simulate on 1024, then usually a new bottleneck arises, because computation and communication do not increase by the same rate. Okay, so there are several performance factors that can be classified, so in sequential ones and parallel ones. So sequential ones you can think of intra-node. So there you do the computation, and to get the computation as fast as possible, it's very important to choose the right algorithm. And to use every optimization you get from your compiler. Then it's also very important to adapt your algorithm to the cache and the memory of your system. So this is a really tough job, and there's not so much tool support here. What is often ignored or not paid enough attention is the input-output, which can be a severe performance limiting factor. If you go to internode, so if you do, or you need to partition your problem. For example, if you have a weather simulation, you divide your domain in several cubes, and every node then is responsible for calculating temperature and so on for for the own cube, and then after a time step communicate the results to the neighbor. So you need to get this partitioning right so that the load is evenly balanced. Otherwise, you have some waiting time when you communicate between the nodes. Here also you can do some multi-threading across nodes. So in there you have to be careful where to allocate your memory. So if you work with the memory of a more distant node, then this takes much more time than if you work with local memory. So you have to also to be careful with synchronization and with locking. So this can severely limit your scalability if it's not done right. Okay. So if you start to build a new program, you need to keep several things in mind. So you need to choose the right algorithm for your problem, and if possible, use some existing libraries. These libraries are usually highly optimized, and by usually also a team of people, and as a single developer, you usually don't have the resources to beat these libraries. There are exceptions though, but if there are libraries, start with these libraries. You should also go to your compiler's manual and check for flags and directives that can be used to make your code faster. And well, you have to think a lot to find the correct algorithm and to think about what's really going on during the computation and communication. But if you, by thinking, come to a hypothesis, then you have to do some measurement to prove or disprove this hypothesis. So, and with the measurements are the only way to really find the bottlenecks. So with just thinking, finding bottlenecks is a little bit difficult because you usually cannot know all about the details what's going on in a modern processor. Measurements are also very important if you compare several different approaches to solving a problem, and to validate your decisions you made for optimizing your problem. So, and this is an iterative step, so you should do the measurements after every change you did to your application. Okay, but you shouldn't overdo optimization. So this is a famous quote from Charles A. Hoare, but I think it's also attributed to Donald Knuth. So we should forget about small efficiencies, say 97% of the time. Premature optimization is the root of all evil. So this basically means that you should only look at the real bottlenecks. And for example, if you have a loop over 10 iterations, usually it does not make so much sense to use OpenMP parallelization if the loop body just is some addition or something like this. Okay, and what is also a problem with optimization is if you optimize a program, it usually gets less readable, and it's quite easy to introduce some bugs that are really hard to find. So it's easier if you start with a slow but correct program than to debug a fast but incorrect one. And no one is really interested in how fast you can compute a wrong answer. Okay. So there's a workflow for performance engineering that we recommend. So it starts with the preparation of your program. So the idea here is to insert some code, some extra code, some probes, some hooks around the interesting parts of your program. So this is usually, this can be done by instrumentation and also, usually by instrumentation. And if you have this instrumented program, you do then a measurement run. During this measurement run, you collect some performance data and you aggregate this data. Third step is the analysis of the data you collected. There you can calculate some metrics, for example, execution time, number of visits, or bytes transferred. You can identify performance problems. For example, you can see which function took the most time. This is then a good candidate to optimize. And you present the results in different ways. You can have a call path profile, or you can have a trace visualization. And then comes the step where the application developer's knowledge is required, because then you can think about where or how to optimize. So you found the bottleneck during the analysis, and then you do some optimization to eliminate this performance problem. And this is not a one-step process, but you can iterate over this quite often. But at some point, the time you invest in making a program even faster increases not linearly. So you have these 80-20 rules that says that usually a program spends 80% of the time in 20% of the code. So this is the code you should look at. And usually you spend only 20% of the time to get 80% of the total speed up that is possible. So at some point, it's time to stop, because we all have just limited resources to work on optimization. So, and for example, if you have an initialization phase and then you have a computation phase that takes much, much longer than your initialization phase, there is not so much, it makes not so much sense to invest much time in doing the initialization faster. Okay, and here another quote from Knut. If you optimize everything, you will always be unhappy, and this is not what we want. So we want to be happy and stop when it's good enough. So let's go to some metrics of performance. So what can be measured? So if we have a program, we can measure a count. So how often do we visit function foo? We can also look at some durations, how much time it took it to complete the function foo. And we can also look at some parameters. For example, if you use MPI, we can look at the bytes transferred, for example. From these metrics, we can derive some metrics. And so we can have some rates or throughput, and this is often needed to normalize the direct measured metrics. So here, for example, I already mentioned some of them. We have the execution time of a function or of a region. We can count how often a function is called. We can also, when we use hardware counters, get the cycles needed per instruction. And we can also get the number of floating point operations. But here it's not always clear what we mean by this. Is this just math operations or hardware operations, instructions? So this is a metric that you have to be careful with. So the execution time of a function, for example, there you can also have or think of two ways to measure this. So, for example, if we enter a function, we could look at our watch and say, okay, it's now 10 o'clock, and then if the function is finished, we look again at our watch and then take the time duration. This is the wall clock time, and this is what most of the performance tools work with. This includes everything. This includes some waiting time. This includes I/O. This includes some system noise, system jitter, and in time-sharing environments, also the time used by other applications. But this is on HPC platforms usually not the case. But for example, I/O, so there your program can be affected by the I/O of other programs running on the same machine on a different partition, but using the same I/O node, for example. The CPU time, in contrast, there you just get the time used by the CPU to execute your application. So there you have no waiting time included. And so this is, from a performance point of view, we are not so interested in, because we want to reduce the waiting time. And if we don't measure it, then we can't find in the parts of the program that contribute to waiting time. Okay, so I already mentioned this. The execution time is non-deterministic. For example, if you have I/O, or if your application is influenced by the I/O of our other application, or if you have OS jitter, you should do some, you should do several runs and take the average out of it. So, but on some systems, for example, the Blue Gene systems, so there it's quite deterministic, so you don't see so many variations, but this really depends on the system, and you need to do some experiments there. So there's other terminology. This you can view the values in an inclusive or an exclusive way. So here, for example, we have a function foo that does some computation here in the beginning, then calls a function bar, does some other computation, and then just returns. So the inclusive time or inclusive duration here would be the time starting at the beginning and then returning here at the end. So the exclusive time would be just the computation at the beginning and the end, but not the time used by a function call. Usually if you look at a call path profile, you have a tree and you can collapse or open this tree, and this is basically this collapsing or expanding. You switch between inclusive and exclusive display. The remaining of this talk, I will present you the classification of measurement techniques. So here we have, for example, the term profiling, which quite often is used for everything that goes together with performance measurement. But here we will be a little bit more precise. So by asking some questions. So the first question is, how are performance measurement triggered? So there are basically two options, sampling and code instrumentation. And then we ask the question, how is performance data recorded? Then we have profile or runtime summarization. And on the other hand, tracing. And then we can ask, how is the performance data analyzed? And there are also the two options. You can do it online or after the measurement. So let's start with the how the measurements are triggered. Here we start with sampling, but first we look into this program here. So we have a main function. Then we have a loop with 3 iterations, and in the loop we call the function foo and pass the loop index here. So if you look at this timeline here, we start at main. So then main calls foo. From foo we return to main here in the loop type. Then we call foo, but now with argument 1. Foo is a recursive function. It calls itself with parameter 0. Then we return to the first foo, or to the start of the recursion. Then we return to main, and the same is here with foo called with parameter 2, then calls foo of 1 and foo of 0. So this is a representation of the program, and if we do sampling now, we interrupt the program run at defined times. So you can do this with a timer interrupt, with some OS signal or some hardware counter overflow. For example, here, this is the first interruption. At this interruption, we look at the call stack, we record some data, and then let the program continue. So this would be the second one. Now we are in function foo. We walk up the stack, collect all the data, and so on. So here you see the bars. This is additional measurement time. So because we walk the stack, we have to record the data. There we introduce some overhead. This is not specific to sampling. All measurement will create some overhead. So with this kind of technique, you just get a statistical view of the program. So basically, the granularity you can choose from the number of times you interrupt your program. The more often you interrupt your program, the more detailed your measurement gets, but also the more overhead you introduce. So one advantage of this sampling method is that it works with unmodified executables. But it's also quite common that you combine it with the next method, with instrumentation. So where, for example, you instrument the MPI calls or the OpenMP, OpenMP stuff, and then just get some information about the call stack using sampling.